Hello students, I am Mrs. Pragati Mahale, working as an assistant professor at AISSMS Institute of Information Technology, Pune. This video gives you introduction to the Turing machine from the subject of theory of computation from TEIT. Let us see the hierarchy of languages which is followed in TOC. We already know that the regular language is been recognized by finite state machine, and it also uses the regular expression. And we have also seen that the push down automata, it uses the context free language. Now coming to Turing machine can recognize the context-free language as well as the recursive language and recursively enumerable languages. So these are the different languages which can be used and recognized by the Turing machine. So now let us have a study in brief the history of Turing machine. The Turing machine is we can say it is a writing machine, because till now from finite state automata to push down automata, all these machines could only read the information, but a Turing machine can also update the information which is stored in the tape. So it can write, it can modify its own input symbols, and so Turing machine is considered to be more powerful than any of the other finite automata that we have studied. So the conceptual model for the general purpose computers proposed by Alan Turing in 1936. The Turing machine has an unlimited and unrestricted amount of memory. A Turing machine can do everything a real computer can do. Nevertheless, there are problems that the Turing machine cannot solve. In real sense, these problems, we can say, they are beyond the theoretical limits of computation. Otherwise, all kind of real computing problem can be solved by the Turing machine. So the Turing machine, as we said, was developed by Alan. Alan defined the Turing machine as a function, okay, which is computable if it can be computed by Turing machine. So as you can see here, the language M is equal to a raised to n, b raised to n, c raised to n, where n is greater than equal to 0, is not recognized either by finite state automata or by push down automata. Such classes of languages can be solved by the Turing machine. In fact, all the kind of binary operations, all kind of mathematical operations, reverse string operation, multiplications, all such kind of examples which are not possible to be solved by FSM or even push down automata can be solved by our Turing machine. So why Turing machine? So these are certain points because of which we say that Turing machine is more powerful as compared to all the other finite automata. So no memory. For example, like multiplication, we took this example in the earlier slide. It required external memory for remembering the long sequence of input. So Turing machine is the one which comes with the memory. In FSM, the input tape is bounded. So to store long strings, we required unbounded input tape, and the Turing machine comes with unbounded input tape, that too which can be accessible from both the ends. So Turing machine. Tape head is unidirectional. In FSM, tape head is unidirectional. That put restriction in computing of finding palindrome. So we want the tape head should move in both the directions. that is from left to right or right to left. And Turing machine is the only machine which provides bidirectional tape head, and because of which so many problems real time computing is possible using the Turing. To move ahead, tape head is read only for most of the automata, whereas Turing machine, it provides the tape head in both read and write mode. So we can not only read but we can also write into the tape. So we use Turing machine. Input alphabet and the output alphabet are separate. There is no necessity of keeping input and output alphabet separately. Turing machine provides input output on the same tape. Now let us have a look on the model of the Turing machine. So here you can see the Turing machine is represented with a tape which has read and write head and which is unbounded from both the ends, and there is a control unit which has the tape head pointing to one of the cell in the tape from which the input symbols are read. So coming to the components of Turing machine, we have tape with extended on either side of the head. We have a finite control, a tape head, action of moving from left to right or right to left, right? So here you can as you can see the input tape, the tape is divided into the squares which are also called as the cells. Each cell stores one symbols including the blank symbol. The blank symbol is not the part of the input alphabet. Blank symbol, which is indicated by B, it belongs to the set of gamma, that is the set of tape alphabets. Okay, we will come to that point. Initially the head points to the leftmost input symbol and the head reads from the leftmost input symbol. The input sigma does not contain the blank. This is the point to be remembered here, whereas sigma is a finite set of input alphabets except the blank symbol B. Okay, so as you can see that the tape has no boundaries. On both the end is at infinite length, and the action, the movement of the head is from left to right or right to finite control. So which it contains the finite number of states, sorry. Okay, so the finite set of states which is taken from the q is the set of states. The set of states q, it contains three special states, that is the initial state, the halt state, and the intermediate state. Also there could be a reject state. So we always start our computing from the start state, which is denoted by the q0, and it is a halt state is a state in which Turing machine stops all the further operation. So in case it has to reject some particular string, then it can go to the halt state. Intermediate state is the state other than the initial and the halt state. Coming to the tape head, it has read and write head. It always pointed at one of the cell of input tape and provides the communication between the tape and the finite control, right? So this head allows us to read or write on the cells of the input tape. Okay, so this head can move in both the direction, from left or. Now coming to the operation of the Turing machine, or we can say the action. So action, it is also called the move, or we can also say the transition of the Turing machine. So this move is a function on the present state and the present symbol. This action results into three things: change of state, change of input symbols, and movement of the head. So these are the three things which are considered as a part of action: change of state, change of input symbol, and movement of the head. So that these three things can be indicated with the help of the transition function delta. So on left hand side you can see transition function has a present state and the present input symbol. After the transition we can see there is a change of state symbol, there is a change of input symbol, and there is a movement of head. Okay, so this movement is from left to right or right to left. Write a symbol and after that read or write, move the head to left or to the right. So now, and this is how the input string is stored into the tape. And you can see this symbols, they are called as the blank symbols. They can also be written as a capital B, and the head starts at the leftmost position of the input string. So from our input string starts from here, so the head is pointing to the first element of the string. So considering one example for the transition diagram, transition function, as you can see here. So this transition function delta means that the movement of the machine from the state Q by reading the input symbol X results into the new state Q0, and it replaces this X symbol by the Y symbol, and the head, it moves to the right of the tape. This is how we read the transition function in the Turing machine. So here with the diagram we can see the example. We read A, then we replace this A with the new symbol K, and we move the head to left. So this is the transition function. Another example to consider here: initially the head is pointing to B, we read the B. B is replaced with F by writing F in the place of B in the tape, and now here we can see that the tape moves to the right side. Finally, let us come to the formal definition of the Turing machine. Turing machine mathematically can be represented using a tuple of 7 symbols. So here Turing machine M can be represented as Q, which is the non-empty finite set of states. We have sigma, which is non-empty finite set of inputs, Q0 the initial state, F the final state, gamma the set of tape symbol including the blank symbol B. This is the formal definition, and delta represents the transition function, which is represented using the 3 parameters as we have seen earlier: the current symbol, the change of the state, then the change in the input symbol, and the movement of the head, maybe to left or right, or there could be no movement. So this is how we represent the Turing machine. Thank you.